Okay, so the mastery results are up. Let's see if I can find that fast. The pass rate was about exactly half the class passed, and I came down a little bit below 90, scooped up a few that were just under 90. But if that was you, so if you got a score, if you see a number other than 0, that means you passed. If that number is in the 80s, then you have to visit me sometime in the next week. We need to talk about just some issues, but you still passed. If you got a 0, that means you did pass and you're retaking it again tomorrow. Unfortunately, we had the holiday Monday, so this is kind of quick. But what I will do is I'm going to we'll try to get done 5 minutes early today since we went over on Friday, and I have your exams. If you want to look at your exam, it's after class today for 10 or 15 minutes, and then you have time to ask me questions. You can do that, and that's whether you passed or not. Okay, so whether you passed or not, you're free to look at your exam, give it back to me, and then same procedure tomorrow. You're going to be taking it again, and for some reduced amount of points. It won't be anything drastically different than what I said in the syllabus. Okay, but it will be fair. Whatever I decide, it will be fair. Okay. Any questions about the mastery? Okay, then for Friday, so tomorrow, Thursday, quiz and recitation, those who have recitation tomorrow. Friday is another My Math Lab assignment, which is due standard time, 10 a.m. Oh, for this My Math Lab assignment, you're just going to get 1. That means 3 attempts on the first problem they give you, okay, instead of 2. So be aware of that, all right? So you got 3 chances on the problem they give you, and then you can't get credit after that. So if you miss it once, don't rush to try it the second time. Really step back and think about what's going on, and then especially then if you miss it a second time, that might be the time to use the Ask My Instructor. Okay, to use that button on the right. Okay, so I want to do 3 of these, and one of these we could talk about for 15 or 20 minutes. So, but I think what would be better is if I kind of go a little bit quicker through 3 of them. All right? The 3 that most of you attempted and we had the lowest success on, which was numbers 3, 4, and 5, which I think is a good mix of problems. So let's just review again this approach to related rates problems. One disadvantage to this online homework is what I suspect is that students get into what can I do to get the answer? Okay, and then you kind of abandon these recommendations and maybe approaches that I'm telling you in class. And I hope that you would, as the instructor of the course, you would trust me and go for that rather than just what can I do to get the answer to this problem? Okay, because what works on one problem in that way is not going to work on another. So what I'm trying to give you is a way to look at it and approach it that will allow you to solve any of them. So let's review what that was. Approach to related rates. So first of all, what's the centerpiece? What's the centerpiece of these problems? Let me give you a hint. They're called related rates problems. So what's the centerpiece, or what are we going for? What's our goal? Yeah?
We're trying to figure out the rate of the length UC.
No, I'm just talking about any related rates problem. Any related rates problem. Over here to the left, so just ignore this problem for now. What's the centerpiece of any related rates problem? Yeah?
Finding an expression that relates all of the rates together.
Yeah, imagine that. An expression that relates the rates, right? That relates. Now, when you come to a problem, it's not going to say, this is a related rates problem, right? So you've got to figure that out, that you've got more than one rate involved, and that's what we want. So we'll call that A. This is the centerpiece. This is the goal, an equation that relates all the relevant rates. Okay, so the next question we asked on Friday was, where does that come from? Where do we get that? Where do we get this equation that relates the rates? And where does it come from? Steve?
The connection between X and Y.
Okay, if that's what you call them, right? So, so these rates come from quantities that are changing, right? So we need the expression or the equation that relates the quantities, and we're going to differentiate that to get the equation that relates the rates. So as a sub-goal, as our first goal, we're going for B. We're going for an equation that brings the quantities together. And then we know by differentiating that, usually implicitly, we can get the equation that relates the rates. Okay, so here's kind of an approach. So we want to read carefully. The first thing we want to hone in on is what are the applicable relevant rates in the situation. We want to hone in on those. And then we want to, from that, figure out what the corresponding quantities are to those rates. Because we're trying to do what first? A or B?
I'm trying to do B first.
We're trying to get B first. We're trying to get an equation that relates to quantities. So we've got to get these quantities. That's step 2. Identify those quantities, and then we're going to write that relationship. So this, number 3, is usually, or often, the hardest part of the problem. Because it's like, okay, how do I form this equation? So often, this step 3 is the hard part. Step 4, if we have implicit differentiation down, isn't too bad. We differentiate B to get A, the related rates equation, and then from there, it's just solving for the unknown. Okay, questions about this? So this is this average. We're going to do these 3 problems. I'm going to go pretty quick, but this is my approach. What my approach is going to be. Anybody have a question on that? All right, so this one says an ice cube that is 9 centimeters on each side is melting at a rate of 2 centimeters cubed per minute. How fast is the length of the side decreasing? Okay, so our goal is this related rates equation, so we got to know what are the relevant rates here. What is one of the relevant rates?
The side is 9 centimeters.
The side is 9 centimeters. Is that a relevant rate in this question?
Change in volume.
Yep, that's a change in volume. So we can even, since we know, so 2, we can just right off the bat just call that dV dt. Knowing that our corresponding quantity, we're going to call V. All right. How fast is the length of the side decreasing? And so, how about that statement that I just wrote there? 2 equals dV dt. There's something wrong with that. Yeah.
It doesn't take into account the fact that the left hand side is changing as well. So,
But this, as by itself, is it okay or not? What's that? Well, 2 over 1 is 2, so there's no units. So maybe they're saying there's no units.
Well, I can say there's no units because dV over dt doesn't equals 2 centimeters cubed per minute.
Yeah, that's the unit. So okay, so if you guys want the unit, we'll do the unit. So that's just the unit. 2 centimeters cubed per minute.
Shouldn't it be negative?
Okay. Nicholas is saying it should be negative. Yes or no? Yeah. So I was hasty, and that's an easy trap to fall into. This is a decreasing quantity, so the rate is negative. The rate is negative. Okay. How fast is the side length decreasing? Okay. So if we're calling side length S, then we're talking about ds dt, and that's our unknown. And we're expecting that value, if the cube is melting, then we're expecting that value to be negative, right? Also a decreasing quantity S. So that's 1, we got our rates, dV dt, ds dt, and then step 2 would be that the quantities are, of course, V and S. That's the easiest step. And T, but, okay, yeah, and T. It's true. Okay, and then 3. So we need a equation that relates those quantities. So now we look at the context. We're talking about a volume and a side length. What brings those 2 together? How do those related in an equation? Yeah, it's a cube, and this, so we take the side length cube to get volume. Okay, and so now we can do implicit differentiation. Derivative of V is 1 by the chain rule times V prime. Derivative of S something cubed is 3 times that thing squared. Yeah, so I could use dV dt, I could use S prime, so I'm just swapping out notation here. Both notations are fine. Okay, and then so now we've got three quantities in that equation, and which one are they asking for us to solve for? What's the unknown here? The rate of change of s with respect to t. So therefore, with the information in the problem, we need to be able to get everything else, because that's our unknown. So we need to know, do we know what the rate of change of v with respect to t is? -2. Do we know what s is?
9.
Given as 9. So it looks like -2 over 243. Did I do that right? And that's going to be centimeters per minute. Did I do the math right? 81 times 3, 243. Yeah. Okay. Questions on that? Do you see how I walk through this approach? Common mistake, plugging the 9 in here. You can't, if you plug, what happens? If you plug in your quantities values here, then when you take the rate of change, it's going to drop out, because your rate of change is going to be 0. If you're calling a changing quantity a constant, by plugging a number in, you're saying that changing quantity is constant. And so when you take the rate of change, it's just going to get 0. So you gotta hold off. Don't plug anything into this. Don't plug anything in until you can plug constants in. So if there are constants in this equation, it's okay to plug them in. But any quantity that's changing, you don't want to plug in the current value, because you'll get a rate of change of 0 and it'll drop out. Questions on this example? Yeah?
I know it really doesn't matter right now, but isn't that 140?
What's that?
47? The 243, is that right?
81, just 81 times 3, right?
Oh, that's,
Yeah. Cool. Any other questions? All right, let's do the next one. This is the light pole. So let's draw a picture. So here's the light pole. A bulb on a stick. Turn out to be a bulb. Okay, and so then you got this guy. And he's 7 feet tall. 7 foot tall. Okay. Whatever works. So what happens is the light shines, and when it off the top of his head, so his body obviously casts a shadow onto the ground, and the end of that shadow is where the light in line with the top of his head. So a shadow is this right here. And it says he's walking towards the street light at 4 meters per second. 4 feet per second, sorry. And it's 16 feet above the ground. So I'm just getting all the information written down here. 16 feet. And at what rate is the end of the man's shadow moving when he is 10 foot from the base of the light pole? Okay, so we want to, what are the rates involved? What are the rates involved? Because we want to get a related rates equation for those rates. So let's figure out what those rates are first. What's the first rate that comes up in the description?
Speed of command. So
4 feet per second. Okay, so 4 feet per second, let's call that. Yeah, the speed of the man. And so as a derivative, we'll call it x. And so then we'll get to that quantity in a second. So x is some distance quantity that's changing at 4 feet per second. What's next?
Speed of the shadow.
With the rate that when he's, yeah, shadow, okay? And so that's unknown, how fast the shadow's moving. And so we'll call it dy dt. So now we've got to figure out what are these quantities x and y, and what's the equation that relates those quantities x and y. So what is x? So in this picture, what is the quantity x that's changing at 4 feet per second?
10 feet.
Yeah, his feet from the light pole. So let me go with red. So this is our x. Okay, so what quantity y is how fast the tip of his shadow is changing or moving? What quantity y is, so what distance y would have a rate of change that's how fast that tip of that shadow is moving? This is a little tricky. The length of the shadow. Is it the length of the shadow? Is that how fast? So is how fast the length of the shadow is changing the same as how fast that point is moving? So we got a bunch of shape. Aaron, why not?
It's the length of the shadow plus the length of his distance from the light.
How come?
Because it's all in relation to the street light.
Right. If we made y this, then how is y changing? This is moving, right? But the man is moving too. So the rate of change of y, then if y was this quantity here, the length of the shadow would take into account how fast the tip of the shadow is moving, as well as how fast the man is moving, and it wouldn't be just the speed of the tip of the shadow. Does that make sense?
So y is from the tip of the shadow all the way to the light pole?
All the way to the light pole. You see, that's truly how fast the tip of the shadow is moving, how fast that quantity is changing. So it takes the movement of the man out of the picture. Does that make sense? That is a little tricky. But because we don't want to do y to be the length of the shadow, or else it won't work. Okay, so now we need a relationship that brings together x and y. Question 3. What general principle are we going to use to get a relationship between x and y? Similar triangles, I agree. So we can say that y over 16 is equal to, so I'm going to take the ratio of this horizontal to the vertical is the same as, what is the length of the shadow then? Y minus x, 2, 7. So I'm doing this y to 16.
Oh, the whole bottom is y. Okay.
The whole bottom is y, and then y minus x would be the blue, the length of the shadow.
Yes,
So would it work the same if just the blue line was y? Then you did y over 7 equals x plus y over 16?
Yeah, but then the answer to the problem is it would not be dy dt, because the rate at which the shadow is changing is not the rate at which the tip of a shadow is moving, because this end is moving too. So you could set it up that way. It's just that then your dy dt would not be the solution to the problem. Do you see? You'd have to adjust when you got to the rates. Okay, so let's quickly here, 7y equals 16y minus 16x. So I'm going to move this way, so a 9y equals 16x. Is that right? So then we get derivative with respect to t now. We're going on to 4. 16 dx dt equals, derivative is 9 times dy dt. Dx dt is?
I think 4 feet per second.
Is it 4?
Oh, isn't it a negative 4?
Yeah, if we're talking about this quantity x and how that quantity is changing, he's moving this way, that quantity is decreasing. That quantity is decreasing. So again, we need a negative there. So I think then the rate is going to be negative 64 over 9 feet per second. And they even say that. Use the direction in which the distance from the street light increases as positive. So saying this direction is positive. So when you put that rate in, it has to be negative because they've specified that this direction is positive x. So therefore this direction is positive y, and that y is decreasing. Questions on this example? Is this helping?
Yes, it is.
Sweet, okay. Yeah, it takes repetition. It takes, focusing your brain on other things and then coming back to it, and then things start to connect. So, last chance for questions before I erase this stuff. You guys good?
Yeah.
Are you guys good? Are you sure? Okay, here we go. Last one is the sand pile. Okay, sand falls from conveyor belt at a rate of 12 meters cubed per minute. What kind of rate is that? I'm gonna go fast. That's a volume. We'll call it dV/dt. Positive or negative? So it says how fast is the height changing? So what's happening to this pile? What's happening to the volume of this pile? It's increasing, so it's positive, right? Okay. The height of the pile is 3/8 of the diameter. How fast is the height changing? dH/dt. Boom. So we need an expression of V and H. What is it? So you might have to look this up if you don't remember. Pi r squared H. I'll let you know what you would need to know and what I would give you. But yeah, something like this I would give you. Height of the pile is always... So here we've got three quantities, and they tell us something here. They say the height of the pile. It'd be nice to have this equation only in V and H, right? Because those are our rates. So if we could, we'd like to kind of eliminate the existence of R in this equation, and that's what this is for. The height of the pile is always 3/8 of the diameter of the base. Okay, so what they're saying here is 3/8 of the diameter is always the height, so 3/8 of 2 times the radius is always the height. And so we can get radius in terms of height, which is 8h over 6. Is that 4/3? All right, see what happened? So we have our rates are dV/dt and dH/dt. So ideally we want this equation only to relate V and H. So can we get R out of there and maintain this relationship?
Yes.
So that's what this is about. The height is always 3/8 of the diameter. So from that I can get that R is always 4/3 H. So now I can put 4/3 H in there, and now I have this equation that just relates V and H. And I think I'm going to stop there. I think you can take this one from there. Right? So you're going to differentiate. You'll have your dV/dt, and you're going to solve for your dH/dt. And it says when the pile is 5 meters high. So you're going to have H in there. And you're going to have everything you need. So it would make it easier, rather than doing product rule on this, you could do the product rule, but much easier to make it H cubed. 4/3 squared, H cubed. We'll avoid the product rule. Questions on this one? Yeah, right.
For me, the hardest part is the algebra side of it. So I just, if it was asking for how fast, let's say, the diameter was changing.
Okay.
So then we would look for the rate of dr/dt, and then basically get rid of the h in that case. Then.
You mean are you saying how fast the radius is changing?
Yeah. Let's say yeah. So so it just, I guess I'm saying you could do the inverse there, where if you were looking for the changing diameter or the changing radius in reference to height, then you could do all that same manipulation and get rid of the h. Not get rid of it, substitute it for.
Absolutely.
Okay.
So now you're saying your unknown is dr dt.
Yeah.
So you would use this then, and it would be h is 3/4 r, and then you'd have an equation of v and r, and then it'd be dv dt and dr dt.
Like
Yep.
half the time I always feel like, oh, I didn't know I could do that. You know.
Cool. Russ.
So since the 4/3 is with the h in the parentheses, it would be 16 ninths
Ninths.
h squared.
H cubed, right? And then you do 16 ninths if you wanted to use multiple ones. Other questions? Yeah, Janae?
Because when that when you're driving it, since you have like 4 different terms that are all tied together, like you can't use the multiplication. What do you do?
These are all, this is all constant though. 1/3 pi, 16 ninths, that's all constant. Just think of that as one big constant.
Is it constant?
It's a bunch of constants multiplied together, but that just gives you one constant. So all you have is h cubed. All you're doing is a constant times h cubed, really, in the end. Other questions? Okay, what I'm going to do when I post I'm going to post a review set for this related rates, but there's a lot more problems in it for practice. So other ones you haven't seen before. Okay, including these. Okay, so let's go on to this. Okay, so what we're gonna look at is inferring info. We've done this here, we've done this on and off throughout the semester. But knowing what the rate of change is, can we infer or figure out what's happening with the accumulation? Okay, so given rate of change, can we infer or figure out what's happening with accumulation? And that now, this is more, rather than looking at, remember we took our rate of change and we made it a step function and we went through this whole process. So now we're not doing that process. We've got this changing rate and our goal is to figure out what the corresponding accumulation is. Okay, just by what we know about rate of change and how it relates to accumulation. So here's a situation where I've got r of x is the derivative of f. So what kind of function does that imply f is?
Accumulation.
I heard a rate and accumulation, so we better know which one that is. Is it rate or accumulation?
Right.
F. Yeah, it could be a rate, okay? But if we're differentiating this to get a rate, then yeah, so the f would be, at first glance we might think, oh, f is an accumulation function, okay? F is an accumulation function. When we take its derivative, we get the rate function. Okay, so n is the current value of x. And this is showing r of n. Okay, so that's our current x, n. And then r of n is the rate at the current value of x. Okay, so what can you tell me about, at this value of x, -4, what does this rate of 34 tell us about the accumulation function, or about the accumulation? What can we say? I know Chloe knows, but somebody new. Marco, what does a rate of 34 tell us about the accumulation at x equals -4?
Does that mean for small changes of x?
Okay.
That it's, at a -4, the rate, or how y is changing is 34 times x.
Okay. Be confident. That was pretty dang good. Yeah, that was pretty dang good. So he said at -4, for a small change in x, how does the accumulation change? How does y change? Someone else take over. Jonathan.
The y changes 34 times as much as x. So the change x.
As the change in x, right. Okay, so Are we accumulate? How are we accumulating? Are we increasing? Are we decreasing? Are we increasing slowly? Decreasing quickly?
Increasing quickly.
Increasing quickly. For a small change in x, we get 34 times the change in y. So this is relative to a rate of change of 2. This is a very fast, positive, or increasing accumulation here. So what I'm going to do is I'm going to set x, and you're going to look at the interval of x from -4 to 2.5, and you're going to watch what the rate of change does as x increases from -4 to -2.5. Okay, you ready? Watch. I'll do it again. And what's our goal? By watching how the rate is changing in this interval, we want to make conclusions about the accumulation. Okay? By watching how the rate changes in this interval from -4 to -2.5, we want to make conclusions about how the rate is changing. One more time. So why don't you talk to the person next to you. What do you think about the accumulation based on how the rate changes between -4? I'll do it again.
It's not going down, but it's not increasing. Well, yeah, the rate is R. So it's changing anyway here, and it's but like it's, if you look at the beginning, it's -4, 34, right? Now we need to -2.47, so the rates so the accumulation would also say
Okay, so this is the inverse we're going to be looking at. All right, so what do you think? Between -4 and -2.5, tell me what happened to the rate. Jamal, did you see what happened to the rate there?
And it slowed down. It's closer.
Slowed down.
Right. So that's 4 was like 34, and -2 is at 6.3. So as it approached 2.5, the rate became smaller.
Got smaller. Okay. What else can you say about it? So he's saying, does everyone agree that it was decreasing? And what else could you say about the rate?
It's increasing, or the accumulation is increasing the whole time.
So the accumulation, he's saying that the rate is decreasing, but the accumulation is increasing the whole time.
Yep.
Zoe, why is it increasing the whole time?
Because the rate is still positive, and the rate was negative.
Good.
Is the rate of change graph like plateauing? Because it started off going to 34, so it's not 7, so it's the whole plateauing.
Is the rate plateauing?
Well,
So let's just, we're going to say what we know for sure about the rate, and then make conclusions about the accumulation. That's the task at hand. So did everyone see that the rate was positive and decreasing? You see that? Is that right? And so then what can you conclude about f of x? Is it increasing the whole time? We're adding to the value of y. We're accumulating positively, right? Because the rate is positive. So fx is increasing. Can we say anything else about how f is increasing?
at a decreasing rate.
Okay, so let's make sure that we're not going to use these phrases increasing at a decreasing rate and decreasing at a decreasing rate. So we're going to separate the two. So we're always talk about them separately because it's you could have 10 people in a room, and they could all disagree about what decreasing at an increasing rate means, okay? So we're going to separate it out. So first of all, f is increasing, and the rate of change is decreasing. Okay, so f is increasing, and the rate is decreasing. Okay, so what would that mean? What would that? Can you make? Yeah, Steve.
F of x is increasing less dramatically as x increases.
Okay, so visually then, how would the graph turn out if it's increasing the whole way, but he's saying it's increasing less and less dramatically? I like that, less and less dramatically. So what would that look like? Can you draw it with your finger? So really, we've got 3 ways that the accumulation can increase. Like this, that's supposed to be straight, and like this. So A, B, what do you think, Kaylin? If f of x is increasing, but the rate of change of fx is decreasing, is it A, B, or C?
I'm gonna say
He thinks A. What do you think? Yeah? Okay, let's look at the next. Good. Okay, let's look at the next from -2.5 to -1. I'll just keep running it over and over again, and you guys talk. What's happening to the rate, and what can we conclude about the accumulation? Here we go. All right, I'll do it again. Let's keep doing it, and you guys talk.
So now the rate is actually decreasing. Or the rate is decreasing the accumulation now starting to increase. So you're going to have from a positive accumulation to a smaller positive accumulation. Yeah. That's right.
Here we go.
So it's like falling over. Yeah, like
Okay, Brian, what did you see? What's that? No, what happened to the rate? Looking at the values as it changed, what happened to the rate? What's that? So the rate decreased.
Yeah, but still positive.
Agree with that? Connor?
The rate increased.
The rate increased? So did it increase or decrease? We got competing answers here.
I saw a decrease.
You saw a decrease. Let's watch it again.
Looks like it increased until about -1.5 and then started to go the other way.
Here we go. Watch. Watch the values. Oh, hold on. We'll come back. All right. So did it increase or decrease? Both, right? Doesn't it increase at first? It increases at first. So what are we at? We're at 8. Oh. I thought it increased at first. No, sir. Oh, so no, the rate. The rate. Okay, what is it doing? It's decreasing. Sorry, it decreases the whole time. Sorry, it's decreasing the whole time. Okay, my fault. It's not both. Sorry, my fault. I was going by my memory instead of looking myself. Okay, the rate is here. It's about 7, and it decreases the whole way until it gets to -4.8. So Rx is decreasing. And now I want to be more specific. So it's decreasing, and then what else about it?
Negative.
What's that?
Turns negative.
Turns negative, right? So it starts positive and it decreases to 0, and then it continues to decrease and become a larger negative. Okay, so what about the accumulation then? So how can we kind of put, so our x is decreasing, so is the accumulation increasing or decreasing?
Yeah. It's increasing until R of n becomes negative,
He wants it increasing as long as r is,
positive.
so our fx is increasing when r is positive, and then decreasing when r is negative. Okay, so what will that look like? Can you draw it with your finger? Draw it with your finger. Most of you got it. Okay, next part. Ready? Just gonna motor here. From -1 to 0.5. Okay, -1 to 0.5. What happens to the rate? What happens to the rate? So the rate begins negative. Does it increase or decrease at first?
Decreases.
Decreases.
And then
It's all it's zero. And then it starts to change.
How? How does it change?
To increase.
Okay, so the rate is negative and decreasing, and then increasing but still negative. So here the rate of change is, it's messy. Rx is negative and decreasing, then increasing. Is that right? Always negative here? Yep, always negative. First decreasing, getting more negative, then increasing, getting less negative. Okay, so what about f of x?
so initially f of x is decreasing quickly, and then decreasing more slowly.
Decreasing quickly and then decreasing more slowly.
Yeah, or it's right. The decrease is slowing down.
Decrease is slowing down, okay? So, is there something that's true about f of x through that whole interval?
It's decreasing
Why?
because the rate is negative.
Right. Okay? So it's decreasing, and first the rate is getting more negative. So how would it be decreasing at first?
More quickly.
So can you, so watch out for words like that more quickly. You want to, we don't know that. We don't know that. Okay, so we want to use, when we're talking distinguishing, use phrases like more negative, less negative, more positive, and less positive. So f is decreasing, and its rate is what? The rate is also decreasing, getting more negative. So draw it with your finger. What does that look like? Okay, and then fx is still decreasing, but then the rate's getting what? Less negative. So it's still going down, but getting less negative. Right. Okay, so I think, what do we have to start with here? I think you guys said it was this, right? And so what was the anyway, and then you said fx was increasing still, but then it started decreasing. Is that right? And then we said that f is decreasing here, and first of all, r was negative. So the decrease was it was becoming more negative, and then became a point where it was still decreasing, but
Not as much.
right. All right, last part. Oops, what happens now? So what's the rate doing?
It's still decreasing, but to like a point, and it says to increase.
Did you say it's still decreasing? The rate?
The rate is.
The rate is
Rate's still
increasing.
negative, it's increasing.
The rate's becoming less negative.
And then that's more sort of positive.
Okay, so the rate is becoming less negative and then more positive. So Rx is increasing this whole time. And it changes, has a change from negative to positive. So what about f of x? So less negative to more positive. So at first, f of x is decreases, then increases. All right, so let's take a look. So, what do we not know about this? So, we can use the rate to get a pretty good shape for the graph, but there's something definitely here that we don't know. What is it that we don't know from the rate? And so when you say placement on the graph or starting point, so it can be more specific. What's that? Or a value, that's an x value, right? So a would be like -4. So can we be more specific? So Brent, what don't we know about this? Right, so it could start at a different y value, and then what, depending on the y value, what would be the result of the potential of the graph, depending on what y value you start at? Yeah, the whole thing shifted up or down, right? So we don't know where, we got the general shape, but we don't know how high up or down this thing is. Okay. All right, so we'll pick this up. So you have your My Math Lab is kind of assessing all these different relationships between